Welcome back to the Deep Dive. Today, we're plunging into perhaps the most mysterious place on Earth.
Yeah, the deep ocean, it's vast, it's dark, and honestly, it's pretty alien down there.
We've been digging into the sources, looking at the extreme conditions and the kind of life that somehow manages to exist.
And our mission today is really to explore what we do know, which, as you'll see, isn't actually that much.
Right, and the scale of the unknown is just staggering. I found this comparison in the material that really stopped me.
Oh, yeah. What was it?
Globally, we literally know less about the floor of our own oceans than we do at the surface of Mars.
It sounds completely backwards, doesn't it? But the numbers check out. Oceans are, what, 71% of the planet?
Yeah, exactly.
And the sources say only about 20% of the seabed has been mapped and actually seen. Maybe 5%?
5%. So 95% of this massive habitat remains basically a question mark.
Which is where our deep dive begins. We need to define deep, though. Where does it start?
Okay, so the deep ocean zone kicks in around 200 meters down. That's where sunlight really starts to fade, the end of the euphotic zone.
Right, where photosynthesis is still happening properly?
But by the time you hit 1,000 meters, forget it. It's total, absolute darkness and crushing pressure.
Ah, yes, the pressure. That's probably the defining feature, isn't it? Hydrostatic pressure.
So on land, where we are now, we feel 1 atmosphere of pressure, 1 ATM.
But go down in the water, and for every 10 meters, that's about 33 feet, you add another entire atmosphere of pressure.
So let's take a depth, like, say, 3,000 meters. That's not even that deep in the grand scheme of things.
Right, relatively speaking.
You're looking at 300 times the pressure we experience right now, 300 ATMs.
For something like a human body, or anything with gas-filled spaces like our lungs, that's instant implosion, catastrophic failure.
So how did deep-sea creatures just shrug it off? Is it just because they're mostly water?
Well, water itself is nearly incompressible, which helps, but it's more complex than that. The real issue is what extreme pressure does to the essential molecules of life.
Like proteins, enzymes.
Exactly. Those complex structures need to maintain their precise shape to function. Pressure wants to squash and distort them.
So it's not just about being watery. They need some kind of molecular defense.
They do. The sources talk about specialized organic molecules called piezolites. Think of them as like molecular counterweights or stabilizers.
Okay, so these piezolites protect the important stuff, the proteins and enzymes, keeping them working properly even under hundreds of atmospheres.
Precisely. They maintain the cell's biochemical machinery, even in conditions that would, well, turn our insides to mush.
Which brings us to the famous blobfish. You know, the picture, that sort of sad, gelatinous lump?
Right, the internet sensation.
Is its weird look when it's brought up directly because its pressure adaptations fail at the surface.
That's exactly it. Its entire body, its tissues, its molecular structure, it's all evolved to be stable and functional under intense pressure. Bring it to the surface, remove that pressure.
And everything just sort of falls apart.
Yeah, structural and metabolic collapse. It really underscores how hard it is to study these animals. You almost have to go down there to see them as they truly are.
Okay, so we have pressure. What other challenges define this environment? It's cold, right?
Oh yeah, freezing cold. Temperatures hover just a few degrees above freezing point, around 4 degrees Celsius typically.
And dark, as we said, so no plants, which means food must be incredibly scarce.
For the most part, yes. The base of the food web isn't sunlight and plants. It's largely dependent on what's called marine snow.
Marine snow. Sounds nicer than it is, I bet.
It's basically a constant slow drift of organic detritus from the upper layers. Dead plankton, fish scales, fecal matter, leftovers sinking down.
So most creatures are waiting for these tiny scraps to fall from above. That sounds like a tough existence.
It is. Energy conservation is key. But the sources also highlight exceptions. There are oases.
Like hydrothermal vents.
Exactly. These volcanic hotspots on the seafloor spew out chemicals from inside the Earth. And life down there doesn't use photosynthesis, it uses chemosynthesis.
Harnessing chemical energy instead of light energy. A completely different engine for life.
Totally different. So you get these dense communities clustered around vents, thriving on sulfur compounds and heat.
Fascinating. So it's either extreme scarcity and patience or these localized chemical feasts.
Pretty much. But exploring any of it, vents or the abyssal plains, is incredibly difficult and expensive.
I read there's a running joke among researchers.
Oh, the one about space? Yeah. It's genuinely easier technologically and often financially to send probes to other planets than to the deepest trenches of our own ocean.
Which is wild, especially when you consider the deepest point Challenger deep in the Mariana Trench. It's almost 11 kilometers down.
Nearly 7 miles straight down. The engineering needed to withstand that pressure and operate reliably is just phenomenal.
So when we do manage to get a submersible down there, what does it look like? The sources mention things feeling truly alien, like the forest of the weird.
Right. That's a fantastic description researchers came up with. They found these vast fields dominated by glass sponges.
Sponges made of silica, like glass.
Yeah. And they form these intricate branching structures. Under the submersible lights, it looks like a bizarre, fragile glass forest stretching across the seafloor. Definitely otherworldly.
And emerging from settings like that, you find some real giants. We have to talk about the giant squid.
Octopuses ducks. The largest invertebrate on the planet, the biggest one ever measured was nearly 18 meters long. That's like 60 feet.
Mind-boggling size. But the sources really emphasized its eyes.
Oh, the eyes are legendary. They are the largest eyes of any known animal, period. About 25 centimeters across the size of dinner plates.
Why so big in total darkness?
It's about detecting the faintest glimmers of light. Not sunlight, obviously, but bioluminescence.
Ah, the light made by other creatures.
Exactly. Predators moving, prey signaling, even the disturbance of water can trigger tiny flashes. An eye that big can gather those photons from further away, maybe spot a sperm whale, its main predator, or locate potential prey from a distance. It's all about maximizing information in the dark.
Makes sense. Efficient detection. Now, compare that to another deep-sea cephalopod, the big fin squid. Very different vibe.
Totally different. Magnapina species, they look almost ghostly. They're known for dwelling extremely deep.
And their shape is bizarre, right? Long, thin arms.
Incredibly long and thin, yeah. Like strands of spaghetti just dangling down, sometimes meters long. And they have these weird elbow-like bends in them.
How do they even use those?
We're still figuring that out. They're covered in tiny suckers. The thinking is they might passively trail them through the water to snag drifting particles of marine snow, or maybe pluck small crustaceans off the seafloor. A very different strategy from the giant squid. The longest big fin seen was about 6.4 meters.
Taller than a giraffe, just hanging there.
Eh.
Okay, let's shift from giants to, well, the festive weird. Deep-sea jellies.
Ah, yeah, some of them are stunning, like the Hydromedusa from the genus Chrysota.
The sources described it perfectly. It looks exactly like a little intricate glass holiday ornament drifting by. Beautiful reds and purples.
And then you have the ctenophores, the comb jellies, often small, maybe orange-sized.
What makes them comb jellies?
They have these 8 rows of cilia, tiny hair-like structures called cretines running down their bodies. They beat those cilia to move.
And the sources mention they do something cool with light.
Right. When the submersible lights hit those rows of beating cilia, they refract the light like prisms. It creates these shimmering rainbow patterns rippling down the jelly like tiny living disco balls.
Amazing. Even simple life uses light in surprising ways down there. But not everything is festive. Let's talk scavengers. The giant isopod.
Pathenomus giganteus. Yeah, these things are impressive. They look like common woodlice or pillbugs.
They're blown up to the size of a football. About 30 centimeters long.
Exactly. A massive version of their tiny land cousins. They're bottom-dwelling scavengers, the cleanup crew for large food falls, like a dead whale settling on the seafloor.
Okay, so they're big, but they're just cleaning up. What about actual predators? The deep-sea lizardfish sounds nightmarish.
It kind of looks it, too. Bathysaurus ferox, one of the deepest living apex predators we know of. Flat head, big mouth.
And just packed with teeth, right? Like needle-sharp, curved teeth.
Yeah, barbed teeth designed to ensure anything it bites doesn't escape. Definitely has that horror movie monster face. Though max size is only around 70 centimeters, so not huge, but still ferocious in its niche.
And they're not alone down there. What about ghost sharks?
Chimeras. They're not true sharks, but ancient deepwater relatives of sharks and rays, cartilaginous fish.
And they look pretty spooky.
They do. Often pale with large eyes, sometimes long whip-like tails. They grow up to maybe 1.5 meters and cruise the bottom, feeding on crabs, mollusks, worms. Definitely earned the ghost name.
Okay, moving up the chain of hunters. The anglerfish, iconic deep-sea predator.
The ultimate ambush predator, really. Famous for its lure, right? That glowing appendage dangling in front of its mouth.
Which isn't actually its light, is it?
No, that's the fascinating part. The light comes from symbiotic bioluminescent bacteria living inside the lure called an esca.
So the fish provides the bacteria a home, and the bacteria provide the fish Bait.
Exactly, a perfect cooperative strategy. The fish uses the light to attract curious smaller fish or crustaceans right into striking range of its enormous jaws. Saves a lot of energy compared to actively chasing prey in the dark.
Incredible efficiency. Now, the sources hinted that even the anglerfish might get spooked. What scares an anglerfish?
Apparently, the Atlantic midshipman might give it pause. Perichthys plectrodon.
Midshipman. What's with the name?
It comes from the rows of luminous photophores, light-producing organs running along its body. They supposedly resemble the rows of shiny buttons on a naval midshipman's uniform.
Huh. And how does it scare an angler? Ambush.
Yeah, it uses its own ambush tactic, often burying itself in the sand or mud on the seafloor, waiting to snatch prey. Maybe its own light display confuses or deters predators, or maybe it's just good at hiding. Another example of light playing a key role.
It's amazing, all these terrifying, hyper-specialized hunters thriving in the dark and cold.
Yeah.
But the deep sea isn't all nightmares, is it? There's cute stuff, too.
Surprisingly, yes. The weirdness down there isn't always scary. Take the deep sea octopuses.
Like the flapjack octopus.
Octopuses. Yeah, instantly recognizable. It's a serrate octopus, meaning it has webbing between its arms.
Which gives it that flat, sort of pancake shape when it spreads out.
Exactly. And it doesn't use jet propulsion like most octopuses, which is energy intensive. It has these little fins on the sides of its head. Mantle, technically, that it flaps to sort of swim around.
Yeah.
More efficient.
And its color. That reddish-orange seems so visible under submersible lights. How is that helpful?
That's the brilliant part. It's camouflaged through physics. Red wavelengths of light are the first to be absorbed by water.
So down deep where there's no red light penetrating.
Red objects appear black, or effectively invisible against the dark background. The octopus doesn't need complex, energy-costly camouflage skin like shallow water species. It just is invisible to most deep-sea predators' eyes.
Wow. Hiding in plain sight using physics? That's clever. What else? There's a ghostly one.
Yeah, the Casper octopus. Found incredibly deep, over 4,000 meters. It got its nickname because it's almost translucent, totally white, very ghost-like.
And we barely know anything about it.
Pretty much. It's currently unclassified, known mostly just from images captured by ROVs. A reminder that we're still finding things faster than we can formally describe them.
And finally, the champion of deep-sea cuteness. The dumbo octopus.
Octopuses. Everyone loves the dumbo. Named, of course, for those big, ear-like fins flapping away above its eyes.
They use those fins to swim, right? Like the flapjack.
Exactly. They gracefully fly through the water using those fins. But dumbos aren't just cute, they're record breakers.
How so?
Depth. They've been observed reliably down to 7,000 meters. That's over 4 miles deep. It makes them the deepest dwelling mollusks ever encountered.
7,000 meters. That's just astounding. So we've gone from crushing pressure and molecular armor
To giant squid with dinner plate eyes, spooky ghost sharks, anglerfish with bacterial headlights.
and ended up with pancake-shaped and elephant-eared octopuses hiding using physics. What a journey!
And remember, this incredible, almost unbelievable collection of life forms comes from exploring just, 5% of the deep ocean?
5%. It
Yeah.
really does boggle the mind. If this is the kind of weirdness and adaptation in the tiny fraction we've managed to glimpse.
Imagine what biological wonders, what entirely new ecosystems are waiting in the other 95%. The potential for discovery is immense.
And it's not just about curiosity, is it? The sources emphasize the ocean's role. It's fundamentally our planet's life support system.
Absolutely critical. You hear that phrase, every other breath we take comes from the ocean. It's tied to oxygen production, climate regulation, nutrient cycles. We need to understand it.
So thinking about that vast unknown, the extreme physics down there, the unique chemistry, what fundamental rules of biology, or even physics as we know them, might already be bent or broken by life we haven't even discovered yet? That's the big question, isn't it?
Given what we've already seen in that 5%, it seems almost certain that the deep sea holds secrets that could rewrite some of our basic understanding of how life works, and that's something profound to think about.